So, started. I'm Takuya ASADA. I was worked for previously 3 or 4 years. I'm not really sending many patches, but I did some Google Summer code and send a few patch for network things and also bhyve. And so let's start. What is bhyve? Bhyve is a hypervisor introduced in FreeBSD. It's similar to Linux KVM. It runs on host OS. So host OS is FreeBSD for bhyve, and the license is BSD, and it's developed by Peter Graham and libymmapi. And so I forgot to write it here. It's released with FreeBSD 10, so it's now in the release. So the bhyve is installed by default on latest version of FreeBSD. There is some hardware requirement. It's required Intel VTX and Intel EPT. That means you need Nehalem or later CPU. It's usually i5 or i3, 5 or 7, and some older CPU like Core 2 or cheaper like Atom does not support these features. So this Intel computer does not support bhyve, and ND support is not much in master branch, but it's working in progress. And bhyve does not support BIOS for EFI for now, so we need some special procedure to boot guest operating system. And EFI support is in progress. And, unlike QEMU, KVM, or some other hypervisor, it doesn't have much device emulation. It has minimal device emulation. So it have virtual block and virtual net and comport emulation, but it doesn't have like VGA or USB or kind of things. So, and supported guest operating system is FreeBSD MD64 and FreeBSD i386 and Linux and OpenBSD. So it doesn't support another operating system at this time. Maybe we can add more operating system later, but we doesn't have much for now. And this is how to use it. We need to load kernel module called vmm.ko first. Then we need to load guest operating system using bhyve load command. Then you need to execute bhyve command. This is the user one part of the bhyve hypervisor, and you need to pass some parameters like CPU numbers and memory size, and also PCI Device configuration such as bhyveblock and bhyveload and serial port, and that's it. Then you can get guest operating system screen on the terminal. But this bhyveload command is the operating system loader, guest OS loader, but just for FreeBSD guest. And so that command does not support Linux or OpenBSD, so you need to use another operating system loader to support these operating systems. And grab2bhyve is the loader for it. And this is modified version of grab2, and it runs on host operating system, and it's able to load Linux and OpenBSD, and you can install it using package command or ports. And it's also on 10 release, so you can just install grab2bhyve by package command. Then you can run Ubuntu or CentOS on top of FreeBSD 10. Then, so maybe we can see some demo on Michael's presentation. So I don't do the demo for bhyve. I will go to the more general topic. So virtualization in general. So what is the difference between container and hypervisor? So J is container. It's virtualized operating system environment. It's virtualized it on kernel level. But bhyve is hypervisor. It's virtualized whole machine. So the approach is different. So in container, processes in jail is just a normal process for the kernel. And the kernel do some trick to isolate environment between jails. So in jail 1, you could not see any process on jail 2, or you cannot see the files or directory on jail 2, but it's all done in the kernel. So the process itself is just a normal process, and the container is lightweight and less overhead, and it's sharing one kernel with all jails. So if the kernel panics, all jail will die. And so it's doing virtualization on top of kernel. So you cannot install another operating system, or you cannot install another version of FreeBSD. So if you are using J on FreeBSD 10, all J is FreeBSD 10. And you won't use Windows or Linux on top of it. Hypervisor is different. Hypervisor virtualizes a machine. So for guest operating system, it looks like real hardware. And so you can install the whole operating system top of the hypervisor. On host OS, virtual machine looks like just one normal process. And so it does not share the guest kernel. It's completely isolated. So you can run full operating system inside of the VM. So you can run Windows, Linux on same time on same host machine. But it's a bit huge than jail. And let's talk about hypervisor. How hypervisor virtualize machine? To make complete virtual machine, you need to virtualize these things: CPU, memory, and I/O. So maybe easiest way to virtualize CPU is emulate entire CPU. It's just like what QM doing or Box doing. So you can emulate CPU on just a normal process, but it's slow and not really useful choice. So if you want to run ARM machine on x86 machine, it's useful. But if you want to run x86 VM on the x86 hardware, it's not a good choice. So if you want to run virtualized x86 on x86 hardware, maybe you want to run get instruction directly on a real CPU, but you need to avoid execute some instruction which modifies system global state or the instruction which perform I/O. So these instructions called sensitive instructions. And if you execute this instruction on a real CPU, it may break host operating system states or guest operating system directly access real hardware. It may break the system. So you don't want to do that. So if the guest OS perform I/O operation on VM, you need to avoid access to real hardware. So in this example, you want to write a character on the display, but you don't want to write the character on real display. You want to write it on virtual display. So you need to prevent execution of the instruction. In this picture, you want to avoid execute out B. How to do that? You can trap the instruction by executing the instruction in lower privilege mode. Like you can run it ring 1 or something, because privileged instruction requires ring 0. Then if you do that, it causes exception, then you can handle it. However, there is some instruction which not possible to trap, because this instruction is not privileged instructions. Therefore, in x86, you need to some more techniques to virtualize x86. I'm talking about the in this time there was no hardware-assisted virtualization, so hypervisor needs to virtualize using some software techniques. On old VMware, they have binary translation technology, which is interpret and modify guest operating system instruction on the fly before the real CPU execute these instructions. So it runs first, but implementation is very complex. It's hard to implement. And there is also another way to virtualize. It was old Zen. Then was released just for Paravirtualization at first. And Paravirtualization is the idea is a bit different. So it modifies guest operating system for the hypervisor. So they change many things on the Linux kernel, then make a special version of Linux just for them. And they also made a hypervisor for the modified version of Linux. It runs also fast, but it's impossible to run unmodified operating systems. So we needed to have more easier and better solutions. So Intel implemented the technology called Intel PTX, which is also called hardware-assisted virtualization. Not on this slide, AMD also have hardware-assisted virtualization, which is called MDB. So I will describe it, the term of Intel VTX. So Intel VTX provides new CPU modes. You will get two modes just for VTX. It's called VMX root mode. It's hypervisor mode, and VMX non-root mode. It's guest mode. It's not related to link protection. It's another thing. So it's if you want to run guest operating system on the CPU, the hypervisor executes instruction for entering VMX non-root mode, which called this operation called VM entry. And after CPU entering VMX non-root mode, it executes guest operating system. And if guest operating system executes some sensitive instructions like out B, in B, so accessing hardware, then CPU stop to executing guest, then exit to the hypervisor, return to the hypervisor. This returning operation called VM exit, which is automatically done by CPU, and hypervisor gets VM exit, then hypervisor can determine where guest operating system stopped and what was the operation the phone at some time. And if it was I/O port access, what I/O port was it? Some kind of information will be provided by the CPU. The hypervisor get this information and do some handling operation for that. If it was virtual hardware access, you need to execute emulation device emulation. So using this feature on CPU, you don't need to implement complex software techniques, and you also don't have to modify the guest operating system for virtualization. And that story was CPU virtualization, and you also need to think about memory virtualization. If you run guest operating system natively, and memory address translation becomes problematic. So if in this picture, if guest B loads page table A, and if the process trying to access virtual page A, virtual page 1, then if CPU use page table A, CPU resolved the page table number as physical page 1. So if you use this one, the CPU will access 1, but you want to map this page here, so it should be 5. So this is a problem. So how to handle that? And there is a software technique to solve the problem. It's called shadow paging. So you need to trap any access of CR3 register which is containing page table address. So if guest operating system want to change page table, the hypervisor trap it. And also guest operating system trying to modify page table entry, also you need to trap it. Then hypervisor creates page table, copy of page table on the hypervisor. So you will have page table A dash, B dash. Then CPU need to refer this A dash and B dash table. So this table called shadow page table, and so in this technique, guest operating system thinking they are using page table A, but hypervisor trap it and tell CPU page table is here, and hypervisor change physical page number like this. So it should be 1 and 2, and so with this, if guest OS A access virtual page 1, it will be access to physical page 5. So it can be implemented or in the software in a hypervisor, and it works well, but it's slow. But so there was a CPU. You only have a choice to use this technique, but recent CPU has hardware assist for memory virtualization. It's called Intel EPT, and with Intel EPT, you have additional page table. It's a bit different from page table, but similar one. It's called EPT, and if you want to run guest OS or virtual machine on VTX with EPT, you need to specify where is EPT. This EPTA. So you need to tell EPT address for Intel VTX. Then EPT have translation table which is from guest physical address to host physical address. So in this picture, you want to map guest physical 1 to 4 to 5 to 8. So EPT goes 1 to 5 to 6, 3, 7, and 4, 8. Then if you set these things on initialization time of VM, MMU translate address by 2 steps. Then hypervisor doesn't need to drop anything. Hypervisor doesn't need to do anything on guest operating system running time. So it will much faster than shadow paging. But this feature was not included first generation of Intel VTX enabled CPU. So for example, Core 2 series does not have EPT, so not always available on Intel CPU, but it's much faster and very useful. Also, you need to think about I/O virtualization. To run unmodified operating system, you need to emulate all devices what you have on real hardware. Not all, but you need to some of to run unmodified operating system. It will be serial ATA and network device like E1000 and USB like EHCI and standard PCI device, and interrupt controller. It must you must have it to virtualize any kind of devices. So you need at least local epic and I/O epic, and also some clock devices, HBET, or maybe you need more another clock source and comport and etc. etc. So you need to have these things to run unmodified operating system ports. You need to devices which is drivers available on guest operating systems, but emulating real devices is not very fast. So if it's very slow device, doesn't matter, but if it requires very fast performance, it will be very bad. And why it's not very fast? Because it causes a lot of VM exits. VM exits is hardware access swapping feature. What is I just described the slide, and it's not ideal for virtualization. So you can have Paravirtual I/O device. So Paravirtual I/O device is the device designed for virtual machine, and it's usually much faster than emulating real devices. But unlike device simulation, you need to have device driver on best operating system. But there is a standard Paravirtual device called PART-IO. Maybe you usually use PART-IO block, PART-IO net. So these things is now become very popular. So many operating system has these driver by default. And a little bit another topic, but it's also related to I/O virtualization. You can attach real hardware on the we call PCI Device passthrough. You can attach the PCI device on VM, but you will have a problem with DNA because the device requires physical address for DMA transaction, but guest operating system doesn't know the real physical address, host physical address. So it's same things of memory virtualization. So you need to translate it. So there is a address translator for the PCI device. It's called IOMMU. In Intel device, it's called Intel BTD. So it's translate guest physical address to host physical address using a translation table. So it will produce MMU between PCI device and memory. Then it will translate memory access transaction. So will translate guest physical to host physical. It's just like EPT, but for PCI device. So let's go back to bhyve and talk about more internal things on bhyve. So I described about virtualization in general, but how bhyve virtualize a machine. Bhyve uses hardware-assisted virtualization. So now it's only for Intel VTX. Maybe it will be MDP available soon, but we have Intel for now. And it also uses hardware-assisted memory virtualization. So it will Intel APT. So bhyve doesn't implement shadow paging for memory virtualization. So you need to have Intel APT on your processor to run bhyve. Then for I/O devices, I/O virtualization, it does not emulate so many devices. It's basically it's use virtual I/O for block and net, and it also have PCI passthrough, but it doesn't have much device mention. It's only have serial console and serial ATA and some other devices. It's required for unmodified operating system like interrupt controller I mentioned, but that's it. You don't have ESP or PCA for now, and also you don't have E1000 dimension or something like that for now. So it uses basically hardware-assisted features, and it relies on Paravirtual I/O virtualization. So a little bit you don't always able to run bhyve on every machine, and you are not able to run every operating system on bhyve, but it's implementing hypervisor in simpler way. Maybe it will more features on bhyve later. And so let's look at inside of bhyve. So in this picture, this is kernel side, and here is user land, and this is library, and these are commands. So let's describe start for bhyveload. Bhyveload is the best operating system loader. You need a special operating system loader because you don't have BIOS. So before you start virtual machine instance, you need to create VM instance and load guest kernel using bhyveload command. Then you need to run bhyve command, the center of the picture. So this is user run part of hypervisor. It emulates devices, and it also have user interface, but it's not really GUI, but you have console on it. And you also have bhyve control. It's management tool. You can dump registers, or you can get information of why VM dies, the reason VM dies, or you can destroy VM instance using this command. And there is a library called libymmapi. It's very thin layer to interact with kernel module. And we have bmm.ko, which is kernel part of bhyve hypervisor. So starts more description about bmm.ko. This is the kind of driver for Intel VTX or hardware-assisted virtualization. So all VTX feature is only accessible in kernel mode. So bmm.ko handles everything about it. And most important work of bmm.ko is switching CPU mode between hypervisor mode and guest mode. And it also provides interface for user land. So it provides interface for these user land commands, and so it have a device file called the vmm/vmname. So each VM instance have its own device file on the vmm directory. It contains VM instance state. So it can create device file via syscontrol, which is hw.vmm.create, and destroy device file via hw.vmm.destroy. So it means create VM instance and destroy VM instance. And also you can access this device file via standard Cisco like read, write, mmap. You can access guest memory area using this system call. And it means you even can dump whole guest memory by dd command, or you can write memory by dd command. And you also have some I/O control to operate to control VM instance. So you have VM memory, which requests guest memory area. So you need to request memory first using this I/O control. Then you can read, write mmap of guest memory area via this device file. And you also have register access by VM set register, VM get register, I/O control. And most important things is vmm. It runs guest machine until virtual device accessed or some other event happened, which need to trap by hypervisor. And with bmm.api, it's just a library. It's very thin library. It's just if you call VM create function, it just executes syscontrol HWVM create. If you call VM set register, it just invoke IO control, VM set register, etc. etc. It's just kind of a library. And maybe I already described about it before, but more specifically, it's using FreeBSD bootloader, but it ported to user root. It's called user root. So we had load using user root to implement OS loader. So it looks like bootloader, but it runs on host OS, not on virtual machine. So once it called, it does following things. So passing UFS on this image and find a guest kernel and load this kernel to guest memory area and initialize page table, create CDT, IDT, LDT, and initialize special register and set page table address and initialize CDTR, IDTR, ADTR, and also CR034 or more registers for to get ready for 64-bit mode. Then after we have load executed, every VM state is get ready to manage guest kernel on 64-bit mode. So if you run bhyve command after bhyve load, guest machine can start from kernel entry point, which is 60-bit entry point. And so this is the main part of the hypervisor. So it's user one part of the hypervisor. So main most important things bhyve command need to do is it's invoke IO control VM run to entering guest operating system guest machine. Then if VM run returning, it means some event. Usually it is hardware access occur on guest OS. So we have endless virtual devices. So it have device emulator on it, and also it have console on standard I/O. So it's image or main loop in bhyve command. So it continues into execute VM run, then handle the event. Typically it's emulating device. So that's it. Any questions?